So welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Xiaowei Fan from the University of Arizona to give the talk this week. Xiaowei received his bachelor's degree from Nanjing University in China, and then a PhD from Princeton in 2000. He was a postdoc at the Institute for Advanced Study for just a year or two before becoming faculty at the University of Arizona, where he is still today. Well, I think calling in today from MIT, where I think you're on sabbatical there. Is that right, Xiaowei? So Xiaowei has really developed this entire field of high-redshift quasars from the early days of, maybe we'll hear a little bit about the history, with Sloan, and then now the latest frontier with James Webb. In addition to his science, Xiaowei is a keen marathon runner. We've run a marathon together, in fact. So it's great that.
You were much faster than me.
Anyway, so welcome, Xiaowei, and we look forward to your talk.
All right, thank you, Jonathan. So it's good to talk to you about quasars. So today I'm going to show you some of the more recent results on a number of JWST programs on study quasars at cosmic dawn, basically redshift higher than 5, all the way up to 7.5. What do we learn from them about black hole growth, their connection to galaxy evolution, and larger structure. Because it's only a 30-minute talk, I'm not going to talk about little red dots. I'm not going to talk about reionization, although the same data that we're collecting on these quasars actually also are teaching us quite a bit about little red dots and lower luminosity, AGN or not, and the connection between galaxies and reionization. The result I'm going to show you is mostly coming from this called Erebus collaboration, which I will introduce a bit later. And the names there are the sort of principal people that are associated with this collaboration. All right, so to get us oriented, I will start with this composite spectrum from essentially all the quasars that have been published until a couple of years ago at redshift higher than 5 also, which we sort of summarized in an annual review paper with Eduardo Benados and Rob Simcoe. Right around the time when JWST launched, we wanted to sort of have a benchmark of what we learned, of what we know about these objects before JWST certainly is going to revolutionize our view about them. So a few things to point out here. Of course, this is basically one-dimensional spectra, sort of from far optical to near infrared wavelengths, of more than 1,000 quasars at redshift higher than 5 also stacked on each other and ordered by redshift. So you see the lemma alpha line now, of course, all the way going to 1 micron beyond. So your ultraviolet emission finally is firmly in the infrared. And then a few things I want to point out is, first, these objects are extremely rare. The sample that we're talking about here, few hundred objects of those redshifts, is really collected from the old sky survey, the entire like high latitude sky. And you can see that curve here tells you that when you go to redshifts, especially beyond 7 also, these things are very hard to find. There are a few of them on the sky. So we're really probing into sort of the very earliest growth of these very massive black holes and the system around them. The second point is that even though these are very early on, the universe is very young, these broad emission lines you see here, not only lemma alpha, but silicon, carbon, and if you look at infrared wavelengths, as I will show you later, magnesium ion lines, it remain to be very strong when you go to the highest redshift. So this system has a lot of chemical enrichment going on already at the highest redshift. And that tells you early black hole growth and galaxy formation are connected. And the third point is on the blue side of the landmark emission line. What you see, of course, are completely dark regions. These are the intergalactic absorption as we are moving towards the epoch of reionization, which is really the feedback, in fact, from the early galaxies and quasars. And of course, when you go to somewhat lower redshift 5.5 also, if you stare carefully, you will see some light coming through again as the universe going from quite neutral to mostly transparent and highly ionized as those redshift. Again, I'm not going to touch more about reionization today. The reason that we would like to study those objects, first of all, understand them in the context of galaxy evolution. In particular, how do we grow from the black holes or in early universe and their host galaxies to sort of the scaling relation between black hole and galaxies that we observe today, whether black hole grow first, whether they co-evolve in some statistical way, or whether galaxies assemble first and black hole catch on. I think you'll not be surprised if I tell you at the end of the talk that the real picture is complicated, that there are multiple sort of pathways to go from high redshift to low redshift. But it's really sort of the physical processes that you see as we study them that make these objects really interesting. That is because quasars really are impacting galaxy evolution over a very large range of spatial scale and actually temporal scale as well. We start from the region very close to the central black hole, where observations of quasars, their broad lines, their accretion disks, some X-ray to optical and infrared wavelengths, is telling us about the seed and the growth of the early supermassive black holes. Few order of magnitude larger scale, we're looking at quasar host galaxies and look for signs of quasar feedback, whether quasars impact the galaxy assembly. Yet another few order of magnitude higher, a larger spatial scale, we want to know what kind of larger scale environment the quasars living in and how they impact or anchor the earliest large scale structures. I'm going to touch on all these three scales in today's talk, but mostly focusing on the galactic scale and the large scale structure. On a smaller scale, let's first start with this spectrum, which is still the highest redshift luminous quasars we know today. I should say that I'm probably not allowed to tell you exactly what the results are, but with new surveys such as Euclid coming on, we will certainly expect the quasar frontier to be pushed towards even higher redshift very, very soon. But this is the highest redshift published luminous quasar, which we discovered a few years, 4 years back. What you see here is an object at redshift 7.64. A few things again to point out. One is this bond here, that's the magnesium-2 emission line from the quasar. This is a line that is very useful to measure the black hole mass of the quasar. Basically, you have you're assuming the width of the line as the gravitational velocity around the black hole, so v squared. And then there is a relationship established lower redshift between the size of broadline region and the luminosity, sort of just a photoionization, L to the minus mod to the 0.5. Then you get a black hole mass calibrated again against local objects. And just based on this measurement, this object is anchored by and powered by a 1.5 billion solar mass black holes, more or less shining at the Eddington limit. So that's an indication that even 700, 800 million years after the Big Bang, you have billion solar mass black holes already. The second point is that when you look at this part of the spectrum, you will see it is not smooth. There are a lot of absorptions, very broad. These are actually absorption coming from silicon-4 or carbon-4 with extremely high velocity, up to a 10% or 20% the speed of light. These are essentially broad absorption line systems that are disk winds or outflows that are very close to the central black hole. So you see early sign of potential impact from black hole accretion to galaxy formation already. Of course, that's only one object. When we look at the sample of quasars at redshift sort of 7 also together, this is from a paper again a few years ago when we collect all the black hole masses that we were able to obtain from the ground-based observations at those redshift. These are objects between 10 to the 8 to few times 10 to the 9 solar masses. And when you plot them on the plane of black hole mass versus photomagnetic luminosity, you will see that these objects basically line up around the Eddington limit. Again, the way that we measure black hole mass actually have no assumption about whether it's Eddington or not. These are just come out of the result that tells you that these quasars actually accreting about as fast as you can. Of those redshifts, which is of course the most luminous objects, you expect them to be accreting very fast, compared to low redshift comparison samples, where sort of the Eddington ratio are much more modest. So if you combine the black hole mass with the maximum Eddington rate and ask the question of how fast or how long can you grow them in order to get to the 10 to the 9 solar mass observation that we see at redshift 7 also, then you trace them back as extended growth, as you have probably seen similar plots before. the argument is that the universe is so young at that time, it's very hard to have the initial growth of the black hole to be sort of the remnants of massive stars in the early universe. You just have to, if you're thinking that Eddington ratio means something, then you probably have to grow them from much more massive seeds. And of course, that's something that many of us are interested in. I would argue that these quasars, even though they are sort of the motivation of why we care about these early seed black holes, they're probably not the best system to actually probe them, because we're really talking about 10 to the 9, 10 to the 10 solar mass black holes, those systems. They are not the sort of the beginning of the black hole growth. They're really the end product. The mass of these objects are comparable to the most massive black holes that we see in the local universe. So they're not going to grow that much anymore. Of course, that means in order to actually figure out what are the seeds of these objects, you basically have to go to higher redshift and lower mass in particular to probe the earlier phase of the object. The other thing I want to point out, these are mentioned before, these are objects that are extremely rare. They are not your typical galaxy or black hole systems. So we also want to go to the lower part of the luminosity or mass function to probe more normal systems. And I said, I'm not going to talk about little red dots and other early AGNs from JWST, except to say that the objects that people are detecting, this is some of the early so-called little red dots, presumably are AGN-powered object, a black hole-powered object residing in early modest mass galaxies from some of the early JWST data. These are some of our own data in actually around the quasar field that have these broad-line AGN as well. And this is probably the highest redshift potential AGN, so-called GNV11, which are the objects that the next few years, I think people are going to learn a lot more about their connection to the luminous quasars that we have been studying. All right, so let's move on and focus on sort of the larger scales. I think these are JWST data that we've been collecting extremely powerful. These are things that are the question of what kind of galaxies these quasars are residing in, extremely hard to probe before JWST. These are some examples. You have seen a plot like that before. These are the beautiful low redshift HST results for luminous quasars. They live in very diverse systems. Some of them look like little galaxies. Some of them look like merging systems. Some of them look like have a spiral in it. But when we try the same experiment, even with the best thing we can do with JWST, which simply just cannot detect them because the PSF is large and the object and the system is not sensitive enough. So what JWST gave us is not only the sensitivity or the resolution, but I think actually even bigger reason is because you're going to reference optical, which you cannot, of course, do it on the ground or with HST, where the contrast between the host galaxies and your luminous quasars is much more favorable. Because of this, we are engaged in a number of large, medium, large, small JWST programs in the first few cycles to study luminous quasars in different wavelengths, different observing modes using JWST. And we put together this called Erebus collaboration, some epoch reionization, something with black hole, which, of course, Erebus is the primordial Greek god of darkness. So we saw it as a name suitable for a collaboration study black holes and reionization and dark ages. And the goal is to have a large enough sample of quasars at the epoch and reionization to study these objects in context of galaxy evolution and reionization. So I'm going to just mix all the different programs that this collaboration put together using JWST and show you some of the highlights of the result that we have so far. The first, of course, we just take some spectra of these objects. We have, at this point, have maybe 50 or 50 of the redshift 7 quasar spectroscopy already. And these are some examples of it. The first example is one of the pretty typical redshift 7 quasars that we observe with JWST that now finally extend to the rest of optical wavelengths, H beta and oxygen straight lines, which we'll come back and discuss some of the more non-typical example later on. But one thing that these lines give you a much better or much more reliable or better calibrated black hole masses compared to the ground-based results. And one thing that is reassuring is that the H-beta based black hole masses are fairly consistent with the ground-based black hole masses that we obtained earlier. This just shows you some examples of the JWST data. All the way goes to 20, 30 micron of these quasars. So now you're looking at redshift 7.5 lines on H beta, H alpha, and all the way to Paschen series lines. And you're also looking at the JWST merit spectroscopy, where when you go to beyond 20 micron, the flux is dominated by the hot dust component in the system. Tells you even at those redshifts, the sort of the dust torus, at least for these most luminous objects, already existed. That doesn't seem to be the case for a lot of little red dots, whatever that means. This bottom line and shows you a JWST spectrum of a redshift 7.5 quasar, all the way from lemon alpha to H alpha by combining different JWST observations. But the thing that's really interesting, of course, is the morphology of the host galaxy. That's something that we couldn't do before. And when we look at our sample of quasar host galaxies, redshift 7, what we see is, first of all, these are red stream optical images. Many of them are finally detected. And the second, they show a very large diversity of the morphology among them. Some of them are fairly extended. These are 3 arcsecond by 3 arcsecond, sort of 15 kiloparsec cutoff. Some of them are 10 kiloparsec looking system, very large extended system of multi-component. Many of them, just similar to what we see in the low redshift PG quasars earlier from HST, look like they're in systems that have companions or mergers. Some of them look like they have expansion looking disk-like structures, almost look like a disky galaxies with no obvious companion, but still about a third of them have no detections, either because the host galaxy is too compact or obscured, or they don't have a lot of star formation or stellar mass for us to detect them. Another thing I want to add is that, as far as I can tell, because these are most luminous quasars, so they don't have a wide range of mass or Eddington ratio or anything. But as far as I can tell, there's not much of a correlation between what the spectrum of the quasar look like and what their morphology of the host galaxy look like. They seem to be doing different things or going through different paths. These are probably 3 of the most impressive examples in our sample. The first one is an object that JWST, as well as the ALMA observation in the same scale, using the C+ line, showing a rather complex system with multiple components. This object also happened to be an object in a protocluster environment with a lot of companion galaxies at megaparsec scale. So this object we almost like to call sort of a proto-brightest cluster galaxy looking, an object sit right in the middle of this forming protocluster. The second object, clearly a merger. An object has 2 distinct components, both in the JWST image in the red stream optical stellar light, and ALMA image tracing star formation. The third object is an object, actually one of the largest systems we have so far. The ALMA image shows a rather extended disk-like structure, and when you look at the velocity field of this object from ALMA, you begin to see a very strong velocity shear, seem to be indicating this object is like a massive disk-looking thing with rotational support. But now we have this red stream optical image, which has allowed us and allowed other groups to actually begin to put together a census of their stellar mass. And when you put the measurement of the black hole mass and stellar mass in this kind of mass to mass or lambda sigma-like relation, what you will see is that the luminous quasar we have is and similar to these little red dots, if you believe they're black hole masses, is order magnitude also above the local stellar mass black hole mass relationship, in the sense that they are in overmassive black holes compared to the host galaxy mass. But of course, as many people point out, at least very big part of this is some kind of luminosity bias, in the sense that we are targeting very luminous quasars. Therefore, they are by definition objects that have a very massive accreting black hole in it. Indeed, when you look at fainter quasars in some of the early JWST results, you begin to see they're getting closer to the local relation. So what I see is most likely not a scaling relation that has been established at that time, rather some kind of upper envelope in the scaling relation, in the sense that the molecular mass can be up to 10%, a few percent of the stellar mass already as a system that have the most accurate active accreting black holes in them. The other question is, of course, is we all want to answer what this black hole or the quasar doing to the host galaxy, and the so-called quasar mode feedback has always been long time been invoked as a possible way of quenching the star formation host galaxy, blow up their gas, and sort of establish local and signal kind of relation. Except that quasar mode feedback has been very hard to come by in lower redshift systems. So I'm going to show you a few examples of the high redshift systems where we see actually the quasar mode feedback may be at work. The first example is a rather long, like 10, 15 hour of exposure of one of the redshift 7.5 quasar using JWST near spec IFU observations. The first thing I want to show you, I want to point out, is actually the spectrum itself. This is a 10-ish hour IFU observation. And you see the spectrum and the blue line, the spectrum itself is not a fit. They're just, all the wiggles are real. These are extremely high signal noise spectra, just because JWST is so sensitive to those wavelengths. So that's the spectrum itself. And then when you actually try to subtract the central point spectrum function from the data cube and look at especially oxygen string emission, which had been a typical line to use for this object to probe galactic scale feedback, you will see that there is extra flux in the system, sort of on one side of the quasar, about extend to about a couple of kiloparsec scale, with rather high velocity, a velocity of a few hundred up to 1,000 kilometers per second. So that clearly is a sign of a significant, like one side kind of outflow coming from the quasar, with a velocity that is beyond the escape velocity of the quasars of the host galaxy itself. People had been using these kind of things to estimate what kind of power, kinetic power, that this outflow can have, basically by combining the luminosity of the outflow with their velocity, with the size and so on. Of course, there are a lot of assumptions involved in what kind of plasma they're in, but just using the same standard assumption that people use in lower redshifts, we find that in this system, this is one of our redshift 7.5 luminous quasar, that even though there is this outflow, the kinetic energy associated with outflow is actually not huge, in the sense of it's only less than 1% of the AGN luminosity. So this object is doing something with feedback, but the feedback is probably not enough to get to the few percent volumetric luminosity that people usually invoke in order to sort of blow up the galaxy ISM and stop the star formation. That's one example. But there are certainly a lot more extreme examples. Let me show you one thing about the spectrum. So when we think about quasar or AGN spectrum, this is a textbook template of H beta oxygen 3 lines. H beta, of course, is the broad line, and then you have the narrow line. This is 1 hour redshift 6 quasar spectrum in the same region. There's the H beta. Oxygen 3 look nothing like the narrow line that you see here. In this system, the oxygen 3 is not only broad, it's also very asymmetric, have a very strong blue wing. And actually, when you look at the two-dimensional spectrum of the object, you see that there's a thing sticking out and the oxygen 3 wavelengths on the two lines. So these are indications, actually, these are not only offset in the velocity space, also spatially at kiloparsec scale. So these are signs of extremely strong outflow in this particular system that change the way that you see the lines. This is not even the most extreme example. in this object, which is a JWST spectrum of a redshift 5 or so quasar, the system looked completely not your two narrow line, one broad line textbook picture now. The oxygen stream has a wing extend all the way to almost 8,000 kilometers per second. So that's extremely fast outflow and has a lot of luminosity, therefore probably a lot of mass and a lot of power associated with it. So we are actually looking at our sample of sort of redshift 5 to 7 quasar in terms of their outflow properties. What we find is that about 50% or so amount of this object has thousands of kilometers per second outflows that at velocity higher than the escape velocity galaxy. So these are actually indication that a good fraction of these quasars in early universe have enough outflow to probably do real damage to the star formation, to the ISM of the galaxy. And whether or not these are really indication that these are the systems that result in the quenched massive galaxies that we see. We have been looking detecting the JWST redshift 5 also, I don't know, but they certainly potentially can do that. And the kind of outflow power of these objects is comparable to a few percent all the way up to more than 10% of the editing luminosity at that point. So these are some indication that these quasars are really in the transitioning phase from the blowout phase to the quenching phase and in the early universe. All right, so I'll spend the last few minutes talking about the larger scale structure, whether the correlation between quasars and larger structure now, and megaparsec scale. One of the probably the most generic predictions of high-redshift quasars is that they're supposed to be the most biased and strongly clustered systems. And indeed, when you look at low redshift clustering, these quasars are strongly clustered, much more so than galaxies. But when you go to redshift beyond 5 also, looking at the correlation function of quasars is really hard. And looking at their companion galaxies is also difficult with HST, for example. So that's actually one of our major motivation of our JWST program is to look at the quasar environment. In this case, we are relying on this JWST mode called slit spectroscopy, which is near infrared camera mode, but actually instead of a filter, you have a prism in front of it. So you're just doing completely open field, blind field spectroscopy, all the objects in the field. So all the objects become a rainbow, become a spectrum, and you have redshift in principle of all the objects that you can detect in the field. And in this particular program for the Aspire, we are targeting 25 quasars in this mode. And what we're trying to really capture are these H-beta oxygen stream emitters in the quasar field. And this turned out to be a very efficient way of looking for these galaxies, just because early universe is really dotted with this strong star-forming galaxies. So within 25 field, we have a few hundred of these H-beta emitters. Some of them, of course, are associated with quasars, some in the foreground, some in the background, and you can see their redshift distribution. But you already see here, right? A lot of these H-beta oxygen stream emitters pile up at redshift between 6.5 and 7. And that's indeed exactly the redshift of the quasars we're targeting in the center of the field. So just by looking at this cumulative distribution, you already know that quasars and galaxies like to be with each other. And this is the first field actually we had by looking at using slit spectroscopy. And this shows the quasar in the center with a sort of a more or less linear structure, about a dozen galaxies, all at the quasar field with extremely sort of cold velocity structure with a linear structure expanding to the range of about more than a parsec. So that's an indication that quasar is anchoring a photocluster as of redshift. In, I think, JWST cycle 2, we expand this particular field to 10 megaparsec scale. And what we see is this photocluster actually extend all the way to this mosaic field that we could reach to. So these are indication of photocluster at 10 megaparsec scale now. And when we look at all our different quasars, and just by counting the galaxies among them, what we see is that, again, there is a fairly wide range of the number of galaxies, companion galaxies we detect. But the dashed line is basically the random field average, which supposedly detect about 1 galaxy per field. And in many cases, we detect a dozen or sometimes even 20 galaxies per field. So on average, quasars indeed living in large super overdensities, but that's not always the case. Again, a lot of diversity. And for the objects that are in these early overdensities, they are sort of on the filamentary structure formed by these galaxies with quasars in the middle of this filamentary structure. And the final thing we did is to actually calculate the correlation function by looking at cross correlation of quasar and galaxies. We can do quasar-quasar autocorrelation, but we can at least do the cross correlation, and then we know the galaxy cross correlation. Then we can back out the quasar-quasar correlation function. And of course, the strength of the correlation at this megaparsec scale is an indication of what kind of average dark matter halo they're living in. So this is the cross correlation result that we have for quasar-quasar compared to the autocorrelation of galaxy-galaxy. What you see is sort of visually is that quasars are much more strongly clustered than the galaxies in the same field. Again, quasars living in very dense environment compared to the also biased galaxy distribution at that time. And just based on that, you can actually get a dark matter halo mass just based on the correlation function of sort of a 10 to 12 solar masses, sort of give you another data point of the early indication of probably the first indication of what kind of a halo mass, black hole mass relation these things are. All right, so I'm going to wrap up. I'm giving a very quick tour of what JWST had been telling us about the relation between quasar and galaxy from the seeding to the galactic scale to their being anchoring the logical structures. I think the impression I get is, again, the quasars in galaxies, even though they are clearly interacting with each other, the kind of scaling relation that we see in local universes at that time at high redshift has really not been established. There's wide diversity in the property of quasar hosts and their structures and their logical structure. But I think one of the things that I'm happy about is these JWST result is getting us the connection from the accretion disk all the way to protocluster scales, and sort of a highlight in this particular field that the quasar itself is one of the 10 to the 9 solar mass black holes with a lot of absorption right at the quasar redshift tells you there's disk winds already. And then this object also turns out that IFU observations showing sort of an inflow of gas that you could see over here coming in at kiloparsec scales. And then this object is actually is a fast rotator of an early disk galaxy located in one of the most overdense protoclusters that we know at high redshift. All right, so I'm going to leave you with sort of three impressions that I learned from these objects. One is that these early quasars are sites of early massive galaxy assemblies, as shown from their connection to local galaxies. The second is there have been frequent strong feedback coming through in these quasars through rapid outflows, and third of them is on average they are anchoring the earliest logical structures at the site of the protoclusters. Right, I'll stop here. Thank you.
Great, thank you very much. So we've plenty of time for questions. So if you have questions, raise your hand in the Zoom, please, or here in the room. Let me start by, I always ask this, and I was going to save this to the end, but I want to ask it first. So at this point, you have examined, it sounds like about 100 galaxies that are nearby these high redshift quasars, or maybe more. Is there any evidence for AGN activity in any other system near, in the vicinity of a secondary AGN around your primary AGN in any of the systems yet, either on small scales or in the companion galaxies?
So, of course, things can be obscured, but if you were just taking the face value at kiloparsec scale, no. So at a galactic scale, within the same halo, kiloparsec, 10 kiloparsec scale, no. Of course, at larger scale, these things that I've shown you are in the protoclast environment, so they have more galaxies around them. We do look for little red dots kind of AGN around these quasars. So far, our indication is that there's no more the clustering and megaparsec scales between quasar galaxy and quasar little red dots. There's no difference. So I think that there's no strong indication there is any.
But you have some secondary AGN candidates that are little red dots around you.
Some of the little red dots are in multiple systems. So if you just forget about the luminous quasars, our target, if you're just thinking about the little red dots themselves, we do see a number of little red dots are in merging systems or binary systems or have close companions. Some of them are little red dots as well. Whether they're black holes or not, again, of course, they're still being debated. But the little red dots themselves do seem to prefer to seem to have some of them in with close companions or in multiple little red dot system. At least I know one or two examples of that.
No, but I was hoping to focus on the surroundings of the known high-redshift quasars and then look for secondary AGN around those. And as far as I can tell, you're saying there's not much evidence for that.
There's not much evidence of it.
Great. Richard, you had a...
Yeah, hi, Chowie. A really nice talk, especially the slitless spectroscopy and the host galaxy imaging, which is really a new development. My question is about a slide you showed where, you commented on the overmassive black holes, and then as you went to the fainter quasars, the excess mass over the stellar mass of the galaxy was less significant, and that would seem to make us worried about the masses that are being claimed for the black holes in galaxies, of which, of course, there's a lot of controversy about the use of the local kinematic relations and applying them to high redshift. Do you think there's a lesson here in this figure that warns us that, cases that we've seen in the literature where, the mass of the black hole is 20–30% of the mass of the galaxy and the object is not a quasar, that we should be worried?
So if you look at this plot, I think these points, these are still these are so-called faint quasar, but by local standard, they're still very bright. So they are probably okay. Is when you look down to this part that I worry about the black hole masses.
Right.
So the lower mass, really lower mass objects, or the AGN kind of thing, because I think the relationship they use for measure these black hole masses are quite a lot more assumptions. These are basically the local calibration is calibrated on these objects, sort of piggybacked on them. Their lines are less reliable. So I think it's particular if you don't even know what the bolometric luminosity of these objects coming from, to use this local relation, scalar relation is sort of dangerous. I don't even know which direction it's going to swing to, but I would not take these points of the black hole masses at face value.
Yeah, okay, very interesting. If I could just add a question for a non-expert, could you explain why the magnesium-2 relation is thought to be so much more powerful than the Balmer ones?
Oh no, H beta is better than magnesium-2. So H beta is just because these scalings are, see, if you look at the earlier slides. So these scalings, there are two parts of it. Actually, there are three parts of it. The part that people are more concerned is the size of the broadline region, and the size of the broadline region is calibrated by reverberation mapping. The reverberation mapping is done much better with H beta in the local, so it's better calibrated there. And magnesium-2 is sort of, again, piggyback on top of H beta to get sort of one step further in terms of the extrapolation, I think. So H beta usually is regarded as better, and magnesium-2 is okay. That's just based on local relation. The problem, and then let's come back to earlier question. The problem with H alpha is yet another level of extrapolation, because there's not much of H alpha regression mapping that I know of that can establish this sort of how the luminosity and the calibration is basically off. All the calibration is sort of based on the H beta calibration.
Okay, thanks.
Oh, great. I mean, I was also going to ask about the black hole masses. So so I can believe those error bars. Can I? Perhaps if you can go back to the plot, they're coming mainly from magnesium 2 and H beta.
Yeah.
No, it was the plot that had the
this one.
stellar mass and the black hole mass. Yeah, here. So in the top part, it's both H beta and.
That's a mix. Yeah, the black hole mass are coming from whatever the literature tells you. So they're the mixture of H beta. And they're not that different. So on average, they're okay.
Mm-hmm. And points that are lower down are not using those lines, but something else.
These are based on H alpha.
H alpha, okay.
There's more or less little red dot lines. They're H alpha based.
Right. I was going to ask then, if we believe the black hole mass and the luminosities and so on, how as you know, a lot of people are saying super Eddington accretion must be occurring, and I'm always looking for potential evidence for it. Mm-hmm. But the data sets you have seem to indicate the Eddington limit is real, is it? The objects are crowding up against the Eddington limits?
Yeah.
Can you comment on, can you rule out super Eddington accretion in some sense?
Well, I mean, there are people saying that doesn't really matter, in the sense that, I mean, they don't think that the volumetric luminosity we're getting is correct anyway, in the supermassive scenario. So I think for these quasars, the Eddington limits seem to be there, at least on face value on this plot. And I think one of the interesting, maybe it's anecdote, but sort of a prediction or something, that why you should trust figures like that to some degree, is that there are, at least in a couple of cases I know, actually in 2 cases I know, that the 2 objects that I'm aware of in this redshift range that the point is over here. In other words, the face value are very super Eddington by more than a factor of 4 or 5 or so. Both of them turn out to be lensed. And then if you correct for the magnification, they bring them right back down. So there's some truth in the Eddington ratio measurement, I think, that we have. Because when we look at these objects that are so, I mean, and both of them are prediction in the sense that when we first observed those objects, we didn't know they were lensed. We just look at them to be so well off Eddington, we said, well, they might be lensed. And then we had HSD images, and they turn out both of them have a lensing galaxy right there. So there's some truth in, I think, in the quasar observation Eddington. Whether or not they grow their black hole mass as Eddington limited in the first few decades, of course, we don't observe it, so I don't know.
Mm-hmm. But what is the state of the theoretical? I know you were in at IAS last semester, and I know people out there are working on theoretical models of super Eddington accretion. Are people putting down synthetic populations of quasars with a range of Eddington ratios and predicting, how they should lie in this diagram, and then can you rule out?
I have not seen that. I'm hoping they can give me some better SEDs even for what from the first principle, what these objects should look like. I don't know how far away they are to do that. These I think the simulation they have is still fairly like around the accretion days themselves.
Yeah.
They probably don't have raw line region or anything to it yet. I don't know.
Okay, I'm not seeing any other questions, so we can go back to Richard.
Yeah, sorry. This question that the feedback mechanisms are still being established, that's the message I've written down here in summary of your talk. Does this claim that the energetics is still at a low level compared to what you see later. Does this, I mean, for those of us working on variability, does this influence the variability of these early quasars in any way? I mean, could they be less variable?
The quasars that we have in our sample, they're so massive and the redshift is high enough. There are not a lot of variability in them. I think I'm only aware of 1 or 2 examples that have significant variability among this sample that have been looked at. But again, they're big enough that I think to the 10, 20 year times, when a few year time scale, they don't vary very much. So
right. So is variability then a late time phenomenon, or is it would the same be the case at redshifts 4, 5?
I don't think there is a strong redshift evolution. Is mostly just because the
luminous, massive,
because massive the size is bigger.
Yeah. Okay.
But have you really been monitoring them closely then, and placing quantitative constraints on the variability, or I mean, to what level are you? They must be varying at some level.
Right. So there have not been a lot of monitoring actually. I'm only, as I said, only aware of 1 or 2 objects that have significant variability among the few hundred objects, but that's mostly because of lack of data. But as far as I know, when you go to somewhat lower redshift, there is the structure function of these AGN doesn't seem to have a strong redshift evolution dependent on it. We are looking at the variability actually of little red dots and stuff. That one I can tell you that the variability of little red dot is not as much as, definitely not as variable as they're supposed to be if they are regular type 1 AGN, and put it this way. So we have been now has enough of little red dots with multi-epoch of photometry from either JWST or HST, and they don't vary, or they don't vary that much. There are only a few of them that show strong variability. And if you think about how low luminosity they are, they're supposed to be varying at a significantly higher level than the data have been indicating. Whatever, that just means that the UV light we're looking at is probably not accretion disk dominated.
Okay, we have about 10 minutes left, and there's a number of other topics I'd like to come to. You mentioned that in the spectra, I mean, you can measure the metallicity, can you, of the gas? Is that right? And
I mean, of course you can measure metallicity with this kind of spectrum. These are, I mean, people do that, but I didn't find. I mean, so from very early on, people have been using like the ratio of things like carbon versus nitrogen and all that to measure metallicity and run quality model on it. The basic message is that they don't seem to change very much from lower to higher redshift. Basically, quasar spectrum look quite similar.
Well, I was going to sort of ask a little bit more about that. So even at the highest redshifts, you're not noticing any difference in line ratios or some elements becoming stronger?
I'm not betting on redshift 7, but redshift 5, yes, there's no difference. Redshift 7, I mean, and redshift beyond 5, the data is still somewhat scattered, but on average, they don't seem to change. But there are a few interesting signs that I can see. One is, as I show you here, there are these weird-looking things that don't really exist at low redshift. So one thing to say, I think, at high redshift, the more outliers than low redshift. You can say that but these are not quasars. These are not quasar problems. This is probably outflow anyway. And at the higher redshift, there also tendency of quasars, lemon alpha line to become weaker, which those weak line quasars usually connected to, or people try to make connection to higher Eddington ratios. I think at that level, but it's a fairly subtle connection, so that level things may change. But most of the emission line ratios, they don't really, I don't have the plot here, but they really don't change with redshift. I think I have somewhere there's a plot showing, I can later on show you a plot of things like iron versus magnesium from redshift 0 to redshift 7. They're the same. I mean, you can see the ion here. These are in two dimensions right there.
Great. Well, then maybe we could come to the host of galaxies. I mean, you showed measurements of the stellar mass. What else are you learning about the host galaxies then? Do you have star formation rates, current star?
All right. So yes. So all these objects have ALMA observations. So they're the majority. I think the majority of the more well-studied quasars of the redshift now have ALMA observations there. So you can their star. You could believe the star formation is coming from the the ALMA continuum coming from star formation. Then you do have a star formation rate. They're on average a few hundred solar mass per year.
But how do you know the ALMA continuum is dust? Is it so that could be heated by the quasar itself, or you would just assume it's
well? So there is no correlation, as far as I can tell, between the crater luminosity and the ALMA dust continuum, or very, very weak correlation. So that may argue that it's star formation, maybe not. People generally think that heating, and also the dust region is pretty large. Kiloparticle scale heating, the AGN heating doesn't really, especially in a disk-looking structure, doesn't really work at very large scale. So I think there certainly, people generally just take it as, and the temperature of the dust is not very different between quasars and between galaxies with or without quasars when you have multi-band ALMA observations. So that's probably all an indication that the star formation can be trusted. On an individual level, it's very hard to say, I think.
Well, I don't work in that area particularly, but the ALMA millimeter continuum tracing dust, it surely depends on how much dust you have and how warm it is.
Sure.
So it's this combination, and yeah, it might seem degenerate a little bit to get the star formation rate out of that. But I have to think more about it. Great. Again, people should raise their hands if you have questions, but I have one more topic on the clustering then. If you mentioned trying to constrain you're measuring quasar to galaxy clustering, and then you place a constraint on AGN to quasar to quasar by, because you know galaxy to galaxy already.
Yeah.
And I guess so then is your constraint on quasar to quasar clustering such that you would be able to predict that I should have a certain number of secondary quasars in my field in these protoclusters, and then that could be eventually checked?
I mean, these are fairly large scale. So we are, our data so far is not going to give you the one halo term. They are just a halo clustering. So these are pretty much dark matter halo related. There are certain indications that the clustering on very small scale, sort of within 100 parsec or so, is stronger when you get one halo term. But again, there's just galaxy AGN clustering, not much of a. There, as I said before, I don't see us access an AGN companion quasars there.
Very good then. Well, we're near the hour. Any last questions for Xiaowei for the recorded part before we finish that? And then we can have a more informal chat. Okay, if not, let's thank Xiaowei again for a great talk and discussion.